Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about radiant energy, also known as light energy. So let's get into this. So radiant energy seems to have a dual nature. So at times it has characteristics of a particle, and at times it has characteristics of a wave. And so, because it has these two different characteristics that seem to be contradictory to each other in a lot of ways, it's hard to describe exactly what light energy or radiant energy is. So, in some respects, we take the particle view, right? So, the particle view of light or radiant energy would be radiant energy is a stream of tiny massless packets of energy called photons. So the photon is a particle or a packet of energy that is tiny and massless. So right off the bat, it's kind of confusing and hard to imagine that you have this particle that's massless, and so that's one of the problems in trying to imagine or visualize what light or radiant energy is. But this is the particle view. So it views it as a particle that we call the photon, which is kind of like a packet of energy. And so we can describe or distinguish between different kinds of radiant energy by the amount of energy it has per photon, right? That would be one way. A second way would be to go with the wave view, and sometimes this is helpful and explains some of the characteristics that we see with regard to radiant energy. And that is, as radiant energy moves away from its source, it has an effect on the space around it that can be described as a wave consisting of an oscillating electric field perpendicular to an oscillating magnetic field. So, what the heck does that mean? So, the way you can think of this is, so here we have our light source, a light bulb, for example. And so emanating or radiating from the light bulb is the light or radiant energy. And so what you see here is a wave. And this wave is consisting of two actual waves. It has a wave that is, say, we'll call this the electric oscillating electric field. So we have a wave of an electric field here, and then perpendicular to that in red. So the electric field that's oscillating is blue, and so perpendicular. I did my best to make it look perpendicular. So the red is the perpendicular wave, and that would be the magnetic field. So you have an oscillating magnetic field that's perpendicular to the oscillating electric field, and so this would be the wave view or wave theory of radiant energy or light. And so because of this, it's often radiant energy is often referred to as electromagnetic radiation. So electromagnetic radiation is just another way of saying light. And so again, you can distinguish between different different forms or different forms of radiant energy or radiant or electromagnetic radiation by wavelength. Oops, I gotta fix this. So the wavelength of a wave, it goes from one point on the wave to the next identical point on that wave. So the easiest way to measure the wavelength would be from the top of a crest to the next crest, or the bottom of a trough of the wave to the next trough. So that would be the measure of the wavelength. And so you could identify what kind of radiation you have, whether it's gamma radiation or radio waves or microwaves or something along those lines. You could distinguish those by the wavelength. So you could either do it according to the energy per photon, or you could do it by the wavelength. And so when we're looking at wavelength, there is a correspondence between the wavelength and the energy. And so I have written here that the energy of your light is proportional or inversely proportional to the wavelength. So if the wavelength is smaller, then the energy of your light is greater. If the wavelength is larger or longer, then the energy of that wave is smaller. So it's inversely proportional to each other. And so, again, there's these two characteristics of light or radiation, and this leads to us to believe that it really is neither a particle nor a wave. It's probably something else. Some people seem to think that it's a particle that, when moves, produces wave-like characteristics, or electric field and magnetic field that are perpendicular. So maybe something along those lines. But at this point, this is the best that we can do. Next thing I want to talk about is the range or the spectrum of different kinds of radiant energy and how they differ with respect to energy or wavelength. And so stay tuned in just a moment. Okay, and here are the different kinds of radiant energy or electromagnetic radiation. And so here I have them listed according to, in order of wavelength and or energy level. So there are 6 different kinds of radiant energy, 7 if you include visible light. So on the middle is the visible light, and on each side of the visible light spectrum you have 3 types of radiant energy on both sides. So here is the visible light. Visible light is our rainbow of colors. So here they are in order of, again, according to wavelength and energy of the photon. So you can see here, so gamma rays, this is wavelength. So when you go from wavelength from gamma rays, you can see that this is 10 to the negative 14 all the way to 10 to the 8. So 10 to the 8 is a much larger wavelength. So we're going from very short wavelengths, and we're increasing going up. And then you'll see here that the energy starts at 10 to the negative 12 joules. So this is in meters. So wavelength is in meters, and we're increasing the wavelength. But notice what happens to the photon energy. It's going from 10 to the negative 12, 10 to the negative 16, negative 18, all the way to negative 34. So this is a much smaller amount of energy. So again, the relationship between the energy of the light and the wavelength of the light is inversely related. So smaller wavelengths give relatively larger amounts of energy per photon, and then larger wavelengths give smaller energy per photon. So the order that you should know is starting with the highest. You have the highest energy radiation is your gamma rays, followed by the X rays, and then ultraviolet light, UV light. And then you've got the visible spectrum. And again, going from violet to red, you're decreasing in energy or you're increasing in the wavelength. So violet light has a shorter wavelength and therefore higher energy. Beyond violet is ultraviolet. Ultra meaning beyond. So beyond violet, ultraviolet, then you have violet, and then the next one is blue. So we're getting lower energy, longer wavelength. Green, lower energy, longer wavelength. And until you get to red, red is the lowest energy of the visible light spectrum, and therefore it has the longest wavelength of the colors. And then if you go beyond red, then you have infrared or below red, right? So infrared radiation is lower energy than red, right? That's because it has a longer wavelength. And then followed by microwaves, which still have a longer wavelength, so they're lower energy. And then finally, the lowest energy, longest wavelength radiation is your television and radio waves. So that is the order of the different kinds of radiation, different kinds of radiant energy. And again, you can organize them or distinguish them either by their wavelengths or by the energy per photon. So I hope this is helpful. That's the end of this video. If you like this video, if this is helpful in any way, then please by all means share the video with your friends, like the video, hit that like button. Also make sure you subscribe to my channel, hit that notification bell. When you do, make sure you click all. And finally, put a comment down below in the comment section. Let me know what you think. If there's a topic you want me to talk about, if you have any questions you want me to answer, then please put them down below. I would love to answer those for you or create a video for you that you want. Thanks for joining me and have a great day.